Artificial intelligence and Internet of Things might be considered at the extremes of the technological ecosystem. AI solutions are typically highly demanding in terms of computation and memory, while IoT units are generally characterized by severe constraints on the available memory, computation, and energy. Filling this gap is the goal of the Embedded and Edge AI, which is a novel and promising research area aiming at designing and developing tiny machine learning and deep learning techniques able to be executed on IoT units. To achieve this goal, we will explore the development pipeline as well as approximation techniques comprising quantization and pruning to reduce the computational load and memory demand of machine learning and deep learning solutions so as to be executed on embedded systems and IoT units. So, how can we design AI applications for IoT? Designing an AI application for IoT relies on a development lifecycle that is based on 7 different steps. The data collection phase, aiming at creating a training set representing the specific application problem that needs to be addressed. The model definition phase aims at identifying the best machine or deep learning model for the considered application trained on the collected dataset. The application development phase has the duty to set up the firmware for the IoT units, comprising the IT applications such as the acquisition and preprocessing steps of the data, as well as the machine and deep learning inference step. The developed application is then compiled and built for a given hardware platform, such as a specific family of microcontrollers. After that, the app is flashed to the IoT device that is then ready to run its application, that is acquiring data, processing them through machine and deep learning inference, and providing an output. Finally, monitoring services could be activated and integrated within the IoT units to verify and evaluate their performance over time. It is worth noting that, differently from a traditional personal computer or cloud-based app development, the life cycle for the AI application on Internet of Things is divided into 2 parts from the technological point of view. First, the identification and training of the model are typically carried out in the cloud, where enough computation and memory are available. Second, the IoT units, being characterized by constraints on memory, computation, and energy, focus only on the inference phase of the machine and deep learning models. But what is the hardware-software architecture of such intelligent IoT units? Here, the hardware typically comprises a microcontroller with few kilobytes of RAM, as well as sensors and actuators. Examples of sensors for IoT are environmental sensors, microphones, cameras, and MEMS accelerometers. The software architecture comprises 3 subsequent steps. The preprocessing phase aims at acquiring and processing the data to make them understandable for the next inference step. The machine and deep learning inference aims at applying the trained model on the acquired and preprocessed data. The output of this step, for example, a prediction, a classification, or the detection of an anomaly in the data stream, is then post-processed to make decisions about how to react, such as opening a door, sending a message to the user, or raising an alarm. Examples of AI applications for IoT are the wake word detection, where a specific vocal command is recognized by the IoT device to activate further actions or processing, such as turn on the light. Here, differently from smart speakers, IoT units are able to recognize only a limited, sometimes very limited, set of commands. But here the point is that this recognition phase is directly carried out on the device, without requiring external processing steps or without moving the speech command to the cloud for the processing. Another example is the person detection. Here, images are acquired by a camera and the detection phase is carried out directly on the device. Finally, data coming from MEMS accelerometer can be used to detect and recognize directly by the IoT units gestures made by a person. But how can we design machine and deep learning solutions able to fit the severe technological constraints of IoT units? This is a challenging issue because we cannot just simply squeeze a complex neural network, for example requiring hundreds of megabytes to store its parameters, into a tiny IoT unit. To address this issue, we need three different steps. First, we need to redesign the architectures of our machine and deep learning solutions, and in particular of our neural networks. These new architectures will be able to consider by design the need to reduce the memory and the computation requirements by considering simplified and tiny models. In this field, recently, new methodologies have been proposed to guide the design of such tiny neural network architectures under technological constraints on memory and computation. In addition to tiny architectures for machine and deep learning, approximate computing mechanisms are typically considered to further reduce memory occupation and computational demand. Examples of such mechanisms are quantization and pruning. But this is not the last step in the design of AI solutions for IoT, since quantized and pruned models can be further optimized for a given target hardware platform. This step, which is typically hardware dependent, is typically carried out through an ad hoc compilers integrated with the development toolchains. But let's focus our attention on the approximate computing and in particular on two specific mechanisms, quantization and pruning. Quantization refers to reducing the memory occupation of the weights of a neural network by changing the number of bits used for the representation of the weights. For example, 32-bit floating point weights could be casted into an 8-bit integer representation. This reduces the memory occupation of the neural network, and it could also speed up the processing since integer operations could be faster than floating point ones. Quantization could be carried out during the training or at the end of the training. In both cases, the advantages in the reduction of the memory occupation can be relevant, but these advantages come at the expenses of a possible reduction in the overall accuracy of the quantized model. Pruning aims at reducing the computational load and the memory occupation of a neural network by skipping the execution of some tasks associated with the processing chain. Here, the advantages are quite evident. Reducing the number of layers to be executed allows to decrease both the computational demand and the memory occupation, since parameters associated to those layers must not be stored. Even in this case, advantages might come at the expense of a possible reduction in the model accuracy. Quantization and pruning are typically jointly considered to further reduce memory occupation and computational demand. But are there other ways to further optimize the learning and inference of AI solutions for an ecosystem of IoT units? We'll see them in the next video. Stay tuned.